modeling processes of neighborhood change team. If you want to pull up your slides, Matthew, feel free. This team was co-advised by Dr. Martinez Mori from Industrial and Systems Engineering here at Georgia Tech. This is also, I believe, now in the second semester, might be going to the third semester. We might continue over the summer. That should be decided soon. And yeah, excited to hear about your updates and how you finalize the semester. Please take it away.
Awesome. So our team consists of me and myself, Matthew, Devin, who's unfortunately can't make it today because of time conflicts, Justin and Nitish, both of whom joined us this semester, and we're very happy to have them. And so the outline of this presentation, first we'll go over the background on exactly what issues in the urban world we're trying to address, and our use of Atlanta as a case study. We'll go over the fundamental game theoretic aspects that drive our model, aspects of the game theory in terms of code and math and our methodology, the current status of our project's progress, as well as our research approach and next steps. So I think Nitish will take it away.
Yeah, so here we have like the motivation that kind of drove our project and how we're going about the project in general. So we just have like some of the facts that we know in this field. So infrastructure impacts people. Designs are made with a standard in mind, but the standard could change, and how will that standard change you? And those facts just go into why we're working on this project and how we're gonna be working on this project. So the main issue that is being addressed is gentrification, which is a process where investment and development in lower income neighborhoods can attract wealthier residents, which can lead to rising housing costs. And it can bring improvements like better infrastructure and amenities, but it can also displace long-time lower income residents who can no longer afford the higher rents or property taxes. And this can break up communities, disrupt cultures, and push out vulnerable populations further from job centers. So our project specifically will be, or is, a case study on Atlanta and the Atlanta Beltline. And the reason we chose this is because it's been heavily researched, and along with that, there's a lot of data on certain aspects of the nearby communities before and after Beltline development. And then another really good aspect of the Beltline is that because construction is still going on, we can see specifically the impacts on neighborhoods when the Beltline expands to those specific neighborhoods and nearby neighborhoods. So for the game theory that we're including in our project, we have no regret dynamics, and no regret dynamics is a strategy for repeated decision making where the choices are adapted over time to minimize regret, and regret is just saying that you won't feel bad for not having stuck with a specific fixed strategy the whole time. And as time goes along, your performance in total will get closer to that of a best constant choice in hindsight, even if the environment is changing. And the way that we implement that in our project is that we have agents, and each agent randomly chooses a centroid to move to. And then for the centroid that they move to, there's a cost that is calculated. And we'll go over the cost function in a bit. And for that centroid, the relative probability of moving to that centroid is adjusted based on the cost that is calculated. So here's just an example of like 3 census tracts and how the cost would affect their relative probabilities of moving to them. So for example, in the first census tract, there's a higher cost and the relative probability would go down a lot. And then a smaller cost, relative probability would go down a bit. And then for the last one, there's no cost, but because the relative probability would go up. So meaning that it's more favorable and agents are more likely to move to those tracks in the future.
Here's sort of an overview of what we have in our cost function currently. So this has actually changed quite significantly from last semester. So we've sort of condensed it down to 3 main things, mainly affordability, attractiveness, and community. So affordability essentially is the, census tract affordable for a given agent. Attractiveness is essentially a measure of like a bunch of different things, including upkeep, amenity access, and proximity to the beltline itself. And then community is essentially a measure of how similar the socioeconomic status of a given agent is to its neighbors. And we'll go over this in the next couple slides. Hey, hello?
Oh, sorry, I got disconnected there.
Oh, you guys disconnected?
Yeah. Are you guys able to see my screen?
Yeah, that's good.
Now it's good. Yeah, okay. All right, so moving on. So this is relating to the affordability score that I mentioned in the last slide. So we use census data in order to calculate endowments for each of our agents in our simulation. And so since each simulation has a unique wealth attribute, some agents will have a higher wealth than others. And so instead of assigning these wealths arbitrarily, we use census data uh, in order to assign these wealths to different agents. So for example, if like 10% of Georgia has an income of above, let's say 100K a year or something, then that would be reflected in the income distribution of our agents as well. And so this is sort of going into the affordability score in more detail here. So each census tract in our simulation would have a row or basically a population cap. And so essentially, a row number of agents would be randomly selected from the weighted probabilities in order to assign agents to specific tracks. So that's how we would calculate our affordability score. And so then moving on to accessibility. So first we have to sort of query amenities. And so we do that by querying from Overpass API data. And this was sort of a work in progress this semester where we had some issues earlier this semester with the queries, but we managed to get it to be a lot more consistent in terms of the data. So yeah. And then moving on to attractiveness scores. So this is how we calculate attractiveness. So we sort of combine three different scores that we had last semester into this score. So we have upkeep times accessibility to the 1/beltline square power. And then we see the equations for each of these, the way that we calculate these are shown on screen right now. And so essentially we have attractiveness being a function of how many people live in a certain tract, as well as how many amenities are in that tract and how close that tract is to the beltline.
Yeah, and the third and final aspect of our cost function is community score. And this is just going to be a measure of how similar is an agent's socioeconomic status, which is basically just in our simulation their income. How similar is this to all of the surrounding agents in the surrounding tracks? And for this, we use a formula called Moran's first spatial autocorrelation. This is commonly used for a formula in the world of urban developments and other fields. It basically takes, in a geographic sense, one location and sees how similar that location's metric is to all the surrounding areas. So in the box is just the formula for Moran's first spatial autocorrelation. And the value for this in our cost function is just going to be e to the power of the difference between the agent's income versus the average of its surrounding agents' incomes. So this is just a brief tying it all together. We're not going to go into all of these equations, or these are the equations that we just covered, but this is just showing them all on one screen for convenience. And just as a reminder, cost is just a product of community, affordability, and attractiveness. And so this is the current progress of our simulation. This is a GIF which we produce, and this is one simulation run. And so if you want to run multiple simulations at once, for example, in the screenshot, you see we run for 4 different values of population cap and 2 different values of agent preference, whether they value amenities versus community. Well, running all 8 of those at the full set of parameters takes about 45 minutes. But we are looking for ways to optimize this, and this is definitely a limiting factor that we really look forward to improving on in the next semesters, now that we have a good basis for the back end of our simulation. And the shades in the graph basically show the income of that census tract. And as you can see, Asian populations and incomes are concentrated around the beltline, as is to be expected. And this is just showing how we get our data. As you can see, there's a graph of the Atlanta Beltline, and we get this from OpenStreetMap, which is an online database containing a lot of geospatial data. And so it contains the geography of the Atlanta Beltline, which is how we get our data. And as for our approach and what we actually want to do with this simulation in the world of urban development, well, once we have a simulation that represents the real world, we want to introduce two different policies. We want to see what will happen to the economic status and the economic distribution of Atlanta when, say, we increase the population cap of census tracts within the Beltline. So this might represent changing, the kinds of buildings, the kinds of housing sites, which in turn increases the population cap of the Atlanta Beltline. Because with gentrification, a large limiting factor is the population cap. It's in high demand and limited storage, and that's why wealthier people are being able to afford the areas and displacing others. And so that's called vertical scaling. And as for horizontal scaling, rather than increasing the population cap within a census tract, we're actually increasing the range of the Atlanta Beltline and expanding it to other census tracts. So for this, we're asking what happens once the Atlanta Beltline is complete? And for this, we'll be running our simulation with the full complete Atlanta Beltline, meaning the full loop is complete, which it isn't right now. It's currently under construction. And we'll see after it's complete, what will the economic distribution look like? Will gentrification be a problem? And if it's not, like what changed? And to reach these goals, we implemented both of these features in our code. We have an agent which basically changes the population cap for regions in the Beltline, and it basically tries to find the optimal population cap for regions in the Beltline for all the other agents. And as for horizontal scaling, as you can see in the plots below, it's simply completing the shape of the Atlanta Beltline and expanding it to all adjacent census tracts. As for our next steps, in the interest of time, I'll go over this super briefly. We're basically going to acquire all the hyperparameters. So that's things like the influence rate of the beltline, the distance decay, etc. And we're going to run the simulation in 2013 and see if it predicts the income distribution all the way in 2023. So it's showing that we run the simulation over time. Will it accurately predict the future? And once we know that, we'll then implement the policy interventions, vertical, horizontal scaling, and seeing what the world of Atlanta, the economic distribution will look like before and after these policy interventions, and seeing if we can come up with a solution to gentrification. And that's all. Thank you very much.